We're going to continue our previous example, our cylinder rolling down an incline. We had drawn our free body diagram and found the acceleration in terms of theta and mu right now, but we want to go ahead and get a value for mu. What is the minimum coefficient of friction that allows the cylinder to roll? And I had mentioned that we're going to approach that by looking at the net torque equation on our cylinder as our second equation to get this unknown. So we will be looking at the torque about the contact point to simplify things for us. And so net torque, Newton's second law in rotational form, equals I alpha. So I, kind of the rotational equivalent of mass, the rotational inertia, and alpha is our angular acceleration. Now the rotational inertia for a cylinder is 1/2 mr squared, and that is for the rotation at the center of mass. And so the next thing we want to do is go ahead and figure out what is causing the net torque. And remember, torque is RF sine theta. So we have to have a force. Well, we have three forces. We have to have a force acting some distance away from the center of rotation. There's only one force that's not acting at the center of mass, and that's the force of friction. So the only force that's contributing to the net torque is the force from friction. So net torque is going to be our force of friction, sine theta. And then if we look at our free body diagram, we see that friction is perpendicular to that vector r that points from the axis of rotation to the force. And so we have sine 90. That's just 1. So we can go ahead and drop that. Putting in kind of R specifics, capital R, and then the force of friction we had discussed last video, mu mg cosine theta. All right, so this whole thing is the net torque. Now we're going to set this equal to I alpha. So R mu mg cos theta equals I alpha. And then we can put in I as 1/2 mr squared. So R mu mg cos theta is 1/2 mr squared. And then alpha, what's going to be handy for us here is to put in our linear acceleration. A is alpha r. So alpha is A over r. And so we're going to go ahead and make that substitution in because we have an expression for our linear acceleration. All right, what we want to do next is go through and clean this up, simplify things. If we look, we have m in both sides of the equation. We have r squared divided by r, so that'll just leave r. But then, very, very nicely, we have r on both sides of the equation, so both r's will cancel out. Let's write what we have now. So mu g cosine theta equals 1/2 the linear acceleration. From here, it's going to just be a matter of putting in that expression for the linear acceleration and solving for mu. So left-hand side, I'm keeping the same, 1/2. And then I'm putting in g sine theta minus mu g cosine theta. Minus mu g cosine theta. And now our only variable, what we're solving for, is mu. So it's going to take just a little bit of algebra to do that. I'm going to multiply both sides by 2 to get rid of that 1/2. So 2 mu. Ooh, another thing we can go ahead and do right now, let's get rid of the g's because they're in every term. So 2 mu cosine theta equals sine theta minus mu cosine theta. Let's go ahead and get the mu cosine thetas together. If we add mu cosine theta, we'll get 3 mu cosine theta equals sine theta. And then we can divide both sides. Mu is 1/3 sine theta over cosine theta. But from trig, we know we can kind of write that a different way. Mu is 1/3 tangent theta. And so that would represent the minimum coefficient of friction that allows the cylinder to roll without slipping. So we do get that rolling motion. If it's any less than that, our cylinder is going to slip down the incline. It won't roll. We're almost done, but we want to go back to our expression for A and go ahead and get this in terms of things we know. So we're going to substitute back in 1/3 tangent theta for mu for our linear acceleration. So A is g sine theta minus that whole expression 1/3. I went ahead and rewrote it out as sine theta over cosine theta times g cosine theta. That will allow us to kind of more easily see how it's going to simplify. So g sine theta stays the same for now, but we see that our cosine thetas are going to cancel out on this term. So minus 1/3 g sine theta. So g sine theta minus 1/3 g sine theta. We get a very clean, concise answer, 2/3 g sine theta. And so that represents that linear acceleration of the center of mass of this particular shape of a cylinder rolling without slipping.